And I'm going to share my screen. Okay, should you see my desktop now? Can you see that? Is it clear?
Yes, yes.
Yes.
Okay, very good. Right. So last time I talked about the difference between digital circuits and analog circuits. Remember that inside the computer system, everything is represented in binary. So today I would like to talk about binary number system, okay, and different number systems like binary, decimal, octal, hexadecimal. These are the most popular number systems. How do we do conversions between these different number systems? So binary means that each digit, okay, or everything is represented inside a computer system using only 2 digits. So binary means 2. So a binary digit is also called a bit. So bit means binary digit. Okay, so the digit can be either 1 or 0. Okay, there are only 2 digits. These digits or these bits have no meaning. Inside the hardware, they have no meaning. But the software can give meaning to these bits. So you can use, if you only have a single bit, then you can only represent only 0 or 1, and this will be not useful. Okay, it will not really be useful to only have the single bit. But you can have a group of bits, okay, to represent, let us say, a number, an unsigned integer, or even a signed integer. I'll talk about how to represent signed integers later. Today, I'll talk about unsigned integers, how we can use a group of bits to represent an unsigned integer. On Thursday, I'll talk about fractions, how to represent even fractions, okay, inside with bits, okay? You can represent fractions. You can represent characters, okay? If you would like to represent the letters, let us say A, B, for example, you can represent the characters in Arabic, or you would like to represent symbols, okay? You can represent them with numbers, with bits. Images, sound, everything which is stored inside the memory of a computer system is stored in binary as ones and zeros. So the software gives a meaning to these bits. The hardware only stores the bits, okay? So now, suppose I would like to use 8 bits to store a number. Now, 8 bits is called a byte, okay? So the computer defines a byte to consist of 8 bits. So we can use 8 bits, a single byte consisting of 8 bits to store a single number. So here I have 8 bits, and these are numbered from 0 to 7. So the least significant bit is bit 0, and the most significant bit is bit 7. Now notice that the least significant bit is the rightmost bit, and the most significant bit appears to the left, okay? Since we have 8, they are numbered from 0 to 7. Each bit has a weight, okay? So the weight of bit 0 is 2 to the power 0, which is equal to 1. Okay, the weight of bit 1 will be 2 to the power 1, which is equal to 2, and so on. And the weight of the most significant bit, here it's bit 7, it's 2 to the power 7, which is 128. So each bit has a position inside the number, and it has a weight. Please interrupt me if you have any question at any time, okay? Now, we can take a number in binary, and we can calculate its decimal value. There is a very simple way to obtain the decimal value of a binary number, because each bit has a position and it has a weight. We can simply multiply, okay, the bit value with its weight. So for example, D0 here, it means that digit 0 or bit 0, it's multiplied by 2 to the power 0. So let me use here my highlighter. Okay, so here when I say digit 0, D0 here, that will be bit 0. It means at position 0. So in this example, D0 is equal to 1. This is multiplied by 2 to the power 0. 2 to the power 0 is just simply equal to 1. Now, D1 here, okay, in this example is 0. It is this bit at position 1. It's multiplied by 2. 2 to the power 1 is equal to 2. D2, it's this bit at position 2 will be multiplied by 2 to the power 2. It's 2 squared. It's multiplied by 4, and so on. We continue all the way to the most significant bit. Now, this most significant bit, if we have n bits, and the least significant bit is bit 0, then the most significant bit will be bit n minus 1. In this example, it is bit 7, because we have 8 bits. But in general, it will be actually at position n minus 1. So this must be multiplied by 2 to the power n minus 1. Here's an example. I have the number 1001, 1101 in binary, which is shown here. Now, in order to obtain the decimal value of this number, now this one is equal to what? The least significant one. Students, are you with me?
Yes.
Let me use the eraser to erase this one. Let me just go back here and use my highlighter. Now, this one here, okay, let me highlight it. This one is what?
D0.
2 to the 0 times 0.
This one is just 1. Yeah, this is D0. So this D0, okay, this one is multiplied by 1. It is just 1. This one here is what?
4.
4.
Yes, this is actually multiplied by 2 to the power 2. So this one is equal to 4. This one is what?
8.
Yes, this one is
16.
And this one, it's 2 to the power 7. What's 2 to the power 7?
128.
128. So all what we have to do is just add the weights. So if you add the weights, 2 to the power 7 plus 2 to the power 4, all the way here to 1, you get 157. Okay? So this number is in binary is equal to the number 157 in decimal. Now notice that we skip the zeros because 0 multiplied by anything is equal to 0. Okay? So all what you have to do is that look at the weights of the ones. Look at their position and their weights and just add the weights and you will get the decimal value of the binary number. So this is how we convert, okay, a binary number. We can convert it from binary to decimal.
Doctor,
yes, Fadda.
is this 157 bit or what?
No, it's the decimal value 157. So 1001, 1101 in binary, it's equal to the number 157 in decimal. Okay, so we are converting a number from binary to decimal. Clear? Is this clear?
Yes, doctor. What
so
about
this is the decimal value. What's the question again?
What about the 2 outside the bracket? What's the point of it?
Now, this 2, which is shown outside the parenthesis, indicates that this number here is in binary. This is what I call the radix. So the radix is 2, indicates that this number is in binary. Okay, it's a binary number. And in binary, we only have 2 digits, either 0 or 1. That's it. We don't have anything else.
Doctor,
Further.
decimal value means the normal numbers that we deal with them in normal life?
Yes. So this 1 here, it's 1 multiplied by 100. It's 10 to the power 2. This 5 is 50. It's 5 times 10. And this 7 is just 7. 7 multiplied by 1. Okay, it's just 7. So this is 100. This is 50. This is 7. It's 157. Okay. So now it's actually important to remember this table. These are some common powers of 2. When we deal in numbers in binary, you have to remember what is the power. So 2 to the power 0 is just equal to 1. 2 to the power 1 is equal to 2. Now, this is actually here, you see that these are the weights of the bits inside the binary number. 2 to the power 2 is 4, 2 to the power 3 is equal to 8, and so on. 2 to the power 7 is equal to 128. If you look at 2 to the power 10 here, it's 1024. Okay, this is interesting. It's slightly more than 1000. 2 to the power 10 is slightly more than 1000. It's 1024. So it's important to remember these powers of 2. If you are dealing with an 8-bit number, you can go from 2 to the power 0 all the way to 2 to the power 7. Okay, because these are the weights, okay, of the bits inside the number. So what we have seen in the previous slide is what we call a positional number system. Positional, it means that every bit or every digit has a position in the number. Now, in the past, the Romans have invented their own number system, and they have invented their own numerals. So they used letters to represent numbers. So X, according to the Roman number system, X means 10. So here we have 10 plus 10, this will be 20. V means 5. So here we have 25, and the I means 1. So we have I, so this is 2. So we have 25 plus 2, we have 27. So this is how we write 27 according to the Romans, okay, more than 2,000 years ago. So they used this. They used the Roman numerals, so they used letters to represent numbers. Now, this number system is not positional. So it does not really matter whether the X appears here or here. In both cases, this X is 10 and this X is also 10. Okay, this I is 1 and this I is also 1. Okay, so it's not a positional number system. Whereas the decimal number system that we are used to, okay, for example, this number, this is 27 in decimal, okay? So 27 in decimal, this 2 has a position. This 2 is 20. It's 2 multiplied by 10. And this 7 is multiplied by 1. So this is the number 27. Okay? So depending on the position of the digit, each digit has a weight. So you have the units here, you have the tens, you have the hundreds, the thousands, and so on. So this is why we call it a positional number system. Okay, so the decimal number system is the number system that we are used to. Okay, it's very natural. And the reason why it's natural, okay, people have invented this hundreds of years ago and became very popular, and everyone adopted the decimal number system. So decimal means 10. So we call the radix 10. And why it's called radix 10? Because we have 10 digits. So the digits are from 0 to 9. Okay, these are the 10 digits in the decimal number system. And the reason why we have 10 digits, why people have thought about it, okay, hundreds of years ago, is that because we have 10 fingers. If you would like actually to teach a child about counting, you ask him to use his fingers, right, to count. That's actually how we learned counting in the kindergarten. So therefore, the decimal number system becomes very natural to us. However, for computers, it will be difficult to represent 10 digits using 10 different voltages. So it's easier to use the binary number system. So the binary number system is radix 2. So radix 2, it means that we only have 2 digits, 0 and 1. But each digit will have a position inside the number. So it's also positional number system. So this one is just a 1. This one is a 2. This is just a 0. This one here is an 8. And this one is 16. If you would like to convert it from binary to decimal, we have to add 16 plus 8 plus 2 plus 1. If you add them up, you also get 27. So this number 11011 okay, is the number 27 in decimal. Okay, so therefore we can easily convert from one positional number system to another positional number system. So binary numbers and decimal numbers are both positional number system. They follow exactly the same mathematical rules. Okay. Now notice that the 0 is important. So this 0 is multiplied by 4, indicating that there is no 4 inside it. So it's very important actually that if there is no 4 to insert a 0 here. Okay, so the 0 is multiplied by 4. Okay, so this is why it's not really included in this number. Okay, so this is why you have to write a 0. For example, in decimal, when you want to write the number 10, you write it 1 0. So the 1 here is multiplied by 10, and there are 0 units. So the 0 is very important in the positional number system. Is this clear? Students, are you with me?
Yes, it's clear.
Yes,
but,
yes, clear.
Yes.
Okay.
What after 255?
What is the sorry? What is after?
I mean, the maximum number is 8 digits, each with value 1, right?
If you use actually 8 bits and all of them are 8 ones, the maximum will be 255. If you want to use actually more than 8 bits, 16 bits, you can increase the range. So people actually, for example, inside computer system, they use more than 8 bits. Sometimes they use 16 bits, sometimes they use 32 bits or even 64 bits, allowing you to use very large numbers. Okay? You understand the question? I mean, you understand the
Yes.
answer?
Yeah.
Okay.
Yeah.
Is this, okay. Right. So the more bits you use inside the number, you can actually increase the range of values that you can represent. With 8 bits, you can only represent from 0 to 255. But if you would like to represent more values, okay, a wider range of values, you have to use more than 8 bits. Let us take a look at this number. Now, this number is 2107 in octal. Notice the 8 here. Notice the 8. Now, the 8 here indicates that this number is in octal. So this is 7. 7 multiplied by 1 is just 7. 0 multiplied by 8 is just 0. Now, this one is what? What is this one?
64.
Yes, it's actually 1 multiplied by 8 squared. It's 64. And how about this 2? It's 2 multiplied by what?
8 to the 4.
8 cubed. 8 raised to the power 3. Yes, 3, because it is at position 3. So therefore, it's 2 multiplied by 8 cubed plus 1 multiplied by 8 squared plus 0 is 7. Okay. So now the number here is 1095. I'm getting an echo. So this number 2107 is the number 1095. Now 1095 is the decimal value of this number. Now this is not 2107 because this is not decimal, this is octal. So I just read it digit by digit, 2107. Whereas this number is 1095 because this number is in decimal. Notice that this 1 is multiplied by 1,000. This 9 is multiplied by 10, and this 5 is just multiplied by 1. Notice the 0 here is multiplied by 100 because there are 0 hundreds inside the number. So the 0 is a very important digit, okay, in the positional number system. Okay? Questions about this? Is this clear?
Yes, doctor.
Now we have seen how we convert a number from binary to decimal. We just apply the equation, just we expand it. Here we use the weights as indicated here. So you can take any number which is in binary and you can obtain its decimal value. Let me ask you this question. How do you convert a number from decimal to binary? Any idea? How do I convert a number from decimal to binary? How do I take a number like 27 and obtain its binary value? Convert it to binary. How do I do this?
Divide by 2.
By division. Divide by 2.
Yes, by division. Divide by 2 and what?
Remainder.
Yes, look at the remainder. Exactly. So this is the procedure. So we take a number which is in decimal. We repeatedly divide the decimal integer by 2. It must be an integer, okay? I'll talk about fractions later. I'll come back to fractions and talk about fractions maybe next time. So you divide the decimal integer by 2, and then you look at the remainder. And the remainder, when you divide by 2, there are only 2 possible remainders, either 0 or 1. This is integer division. If the number is even, the remainder will be 0. If the number is odd and you divide an odd number by 2, then the remainder will be equal to 1. So this remainder becomes a bit inside the binary number. Here's an example. Suppose I would like to convert 37. I'm writing here 10 just to indicate that this number here is in decimal. You don't really have to write 10 if it's in decimal because it's going to be clear, okay? But this is just for for emphasis, okay? I would like to emphasize that this number 37 is in decimal, okay? I would like to convert it from decimal to binary. So the way to do it is that you can actually divide 37 by 2. You have to start by dividing 37 by 2. Now, when you divide 37 by 2, you get 18.5. But this is integer division. So you get 18. Now, when you multiply 18 by 2, you get 36. So there is a remainder. 37 minus the 36, the remainder is equal to 1. That's the remainder. Take the 18, divide it by 2, you get 9. And the remainder is 0. Why? Because 18 is an even number. Now take the 9, divided by 2, you get the 4, and the remainder is equal to 1. Why? Because 9 is an odd number. Okay? Continue. Divide 4 by 2, you get 2, and the remainder equal to 0. Divided 2 by 2, you get a 1, the remainder equal to 0. Now 1 divided by 2. Now 1 is less than 2. Okay? In fact, you get 0.5. But we write the quotient to be 0, and the remainder will be equal to 1. Now we stop when the quotient is equal to 0. The first remainder is the least significant bit, whereas the last remainder is the most significant bit. And we stop when the quotient becomes equal to 0. This is when we stop. This is the procedure, okay? Now you can say that 37 in decimal is equal to 100101. Now notice that, let me use here my pen tool. I'm going to switch here to my pen tool. Notice that this one here, okay, is my least significant bit. So I'm going to put an arrow here, and this one becomes the most significant bit. So basically we have discovered the remainders. Okay, so the number now, okay, so the first remainder is the least significant bit, and the last remainder is the most significant bit. So basically we fill these bits from the right and we move to the left. Okay, is this clear? This is very important. Now, if you want, what you can do is that you can convert it back, okay, from binary to decimal just to check that your conversion was done properly. Now, this is 1, this is 4. Now, this one here is 32. It's multiplied by 2 to the power 5. 2 to the power 5 is 32. So 32 plus 5 is equal to 37. So therefore, the conversion was done properly. So you can always check and verify that the conversion was done properly. Is this clear?
Doctor,
yes.
What does number 10 mean?
10 in decimal?
10? Yes, below 37.
Sorry, below 37, you're talking here about this division here? This is 18.
Next to the question.
Yes.
Oh, this 10 here. It means that this is the radix. The radix is 10. When the radix is 10, it means that the number is in decimal. You don't really have to write it because it's very clear. When you write 37, okay, it means it is a decimal number. But I'm writing 10 to indicate that this number is in decimal.
Okay.
That's the radix, okay?
Okay.
Right. Let us move on.
Doctor,
Yes.
I have a question on the previous slide.
Yes.
This 2 after the bracket.
That indicates that the number, it means that this number is
yes,
in binary. You
yes,
have to write
it
to indicate that this is a binary number. That's 100101 in binary.
Yes, but it can be 4 or 6.
Yes, yes, you can actually use different number systems. In this case, I'm converting to binary, to radix 2. But if you would like to convert to another radix, I'll show you another example how to do this.
Yes, like in 4, then division 4, 4, 4, like this.
Yes, if you would like to convert it to radix 4, you divide by 4. If you would like to convert it to radix 8, you divide by 8, and so on.
Okay, I get it. Thank you, Victor.
You are welcome. Okay, so now let us move on. So now suppose, so why this procedure works? Okay, so here I showed you the method, how you divide by 2, you look at the remainder. Now remember that if you have a number n, and this number n is in decimal, and you would like to convert it to binary, I can write n, okay, as dn minus 1 multiplied by 2 to the power n minus 1, all the way here d0 multiplied by 2 to the power 0. Now, when you divide n by 2, you divide everything here by 2. Now, d1 multiplied by 2 divided by 2, you get d1. d2 multiplied by 2 squared divided by 2, you get d2 multiplied by 2. And this is multiplied by dn minus 1 multiplied by 2 to the power n minus 1 divided by 2, you get 2 to the power n minus 2. Now, the remainder will be d0. So after the first division, when you divide n by 2, you get quotient 1, which is equal to this number, and you get the remainder 1, which is d0. So the first remainder is the least significant bit of the binary number. Now you take quotient 1 and divide again by 2. Then in this case, you get this quotient 2, which is equal to this number. And the remainder 2 will be equal to d1. So this is mathematically, this is why the method works. So this is why we divide by 2 repeatedly to obtain the remainders. And the remainder, the first remainder will be d0. The second remainder will be, sorry, d1, and so on. Is this clear? I'm trying here to show to you why this method works, okay? And this is why we have the remainders. These are the bits from the least significant to the most significant. Now, there are some popular number systems, like the binary number system. So we say that binary means the radix is equal to 2. This is binary here. So it means 2. This is the radix. We have only 2 digits, 0 and 1. So we are allowed to use only 2 digits when we are dealing with binary. We are not allowed to use the digit 2 or digit 3. These do not exist in binary. Octal means 8. That means the octal number system. It's also very popular. People use it. Okay, and the radix is equal to 8. So there are 8 digits from 0 to 7. Notice that digit 8 and digit 9 do not exist in the octal number system because there are only 8 digits. So the last digit here, okay, the largest digit is 7. Okay, 8 does not exist. In decimal, we say decimal, it means that the radix is 10. That's the meaning of decimal, okay? And therefore, there are 10 digits from 0 to 9. This is the number system that we are used to, okay? This is the natural number system that we have been taught, okay, since early childhood, okay, since kindergarten. Okay, so when we count in decimal. When we do arithmetic, we do it in decimal. So decimal is natural to us, okay, as human beings. But we don't really use decimal directly inside the circuits, inside the computer system. We use binary, okay, because it's easier to build circuits which are based on the binary number system. Okay, we also have hexadecimal. So hexadecimal number system, it means that the radix is 16. Okay, that's the hexadecimal number system. Now we have 16 digits from 0 to 9. These are 10. They are identical to the 10 digits that exist in decimal. But we need 6 more because we have radix is equal to 16. Now, since we are running out of digits, we have to use letters. So we use the letters A, B, all the way here to F. Okay, these are 6 additional letters that we are using, okay, to represent the 16 digits. So here A is 10, B is 11, and F is 15. Okay, so C will be 12, D will be 13, E will be 14, and F will be 15. So these are 6 extra digits. Now we don't write 10 as 10, we write it as A. It's a single digit in the hexadecimal number system. Is this clear? So these are the most popular number systems, but we can also have other ones. If I would like to have, for example, radix 5, it's okay. You can actually have a radix 5, and you will have 5 digits from 0 to 4. If you'd like to have radix 12, it's also okay. You can go the digits from 0 to 9, but these are 10. You need 2 more, you add A and B, and that's it. This is basically how you can define different number systems. And all of them are positional, and there's an easy way to convert between them. Now, between octal, hexadecimal, and binary, there is a very simple way to convert between these 3 different number systems. Okay, let me show you. Before I do this, let me show you this table here. Okay, the octal and the hexadecimal numbers. So remember that decimal means that the radix is 10. Hexadecimal means that the radix is 16. So notice that the radix here is 10. This is decimal. And for hexadecimal, I'm just writing here hex. It means that the radix is 16. Is this clear? Students, is this clear? Are you with me?
Yes.
Yes.
Okay, good. So I really need to hear your voice. Okay, let us, if you have any questions, you can just interrupt me at any point in time. Type. So in the case of radix 10, we can go from 0 to 9. Okay, these are the 10 digits. Now, if you would like to write 10, there is no digit, which is 10 in decimal. You have to write it as 2 digits. This is how you write 10. It's 1, 0. 11 will be 1, 1. 12 will be 1, 2, and so on. 15 will be 1, 5. This is how we write numbers in decimal. So if you cannot write it as a single digit, you have to use 2 digits. If you can, if the number is larger than 2 digits, larger than 99, you have to use 3 digits. So 100 will be 100, and so on. In hexadecimal, you can actually write 10 as A. Now notice that in hexadecimal, the first 10 digits from 0 to 9 are identical to those which are used in decimal. But 10 becomes A, 11 becomes B, 12 becomes C, and 15 becomes F. These are 6 extra digits that we use in hexadecimal because we must have 16 digits. So therefore, we use letters, okay, A to F, to mean digits, okay, in the hexadecimal number system. Now, if you want to represent them in binary, we are allowed. Binary means radix 2. That's actually is binary, okay. In order to represent a hexadecimal digit in binary, we need 4 bits. So 0 in hexadecimal becomes 0, 0, 0, 0 in binary. 1 becomes 0, 0, 0, 1. 2 becomes 0, 0, 1, 0. Notice that 1, 0 in binary is decimal 2. 1, 1 becomes 3, and so on. Notice that 9, before 9, 8. 8 is 1, 0, 0, 0. 9 is 1, 0, 0, 1. 10 is 1, 0, 1, 0. 1, 0, 1, 0 is the digit A in hexadecimal. And finally, 15 is 1, 1, 1, 1. This is the digit F in hexadecimal. So you can see that hexadecimal, which is radix 16, is related to radix 2. Notice that 2 to the power 4 is equal to 16. And this is why we need 4 bits to represent a single digit in hexadecimal. Notice that F is 1111, so this is 8 plus 4 plus 2 plus 1. This will give me 15, and 15 is the digit F. In octal, we have from 0 to 7, which are identical to those in decimal, but 8 becomes 10 in octal. So this 1 here is the 8. 9 becomes 11. It's 8 plus 1. 10 is 12. It's 8 plus 2. And 15 is 17. 8 plus 7 is equal to 15, which is the digit F in hexadecimal. This table is very important, and it's very important to memorize this table when you would like to do quick conversions between octal, binary, and hexadecimal. Okay, let me show you an example. So remember that binary, octal, and hexadecimal are related. The radix 16 is equal to 2 to the power 4. So for this reason, every digit in hexadecimal will be equal to 4 bits in binary. Now radix 8 is equal to 2 to the power 3. So every digit in octal is equal to 3 bits in binary. So we can actually group these bits, starting at the least significant bit, and we can actually do the conversions, okay, from binary to octal and from binary to hexadecimal. Here's an example. Suppose I have this 32-bit binary number, okay? So this number consists of 32 bits. I selected these bits randomly. Some of them are 1, some of them are zeros. This is just one number, okay, in binary. It consists of 32 bits. How do I convert this number to octal? Students, are you with me? How do I convert this number to octal? Anyone?
By grouping, yes.
By grouping.
Well, how do I group them?
From right to left.
Yes.
8 by 8.
Well, I would like to convert it to radix 8. So the group will consist of how many bits?
3.
3 bits.
Yes.
Okay, so therefore we start from the right, we move to the left, we take a group of 3 bits. So this 100 becomes what?
4.
4 in octal.
Yes.
Then we have 010.
2.
Okay. Next we have 110.
6.
011.
3.
Okay, 010.
2.
101.
5.
Again 101. Another 5.
5.
000.
0.
Exactly, it's just 0 in hexadecimal. Sorry, it's 0 in octal. We are doing it in octal. 011.
3.
And 101. It's another 5.
Yes.
And finally, we have 11.
We had 0.
So we can insert the 0 to the left. This does not change the value of the number. So 011 is what?
3.
Exactly. Right. Now let us convert it to hexadecimal. I need another student. Okay. Another student. Okay. Let us do the conversion to hexadecimal, from binary to hexadecimal. How do I do this? Who is going to volunteer? Someone, please. Students.
It should be every
yes,
4.
Abdullah.
But every 4.
So we are going to group them as groups of 4 bits. So let me start with 0100. This is what?
4.
4, yes. How about 1001?
9.
This
9.
group, yes, 9. How about 0111?
7.
7. 1010.
10.
What is 10 in hexadecimal?
A.
I have to write as a single digit. 0110.
6.
Okay, good. Next one.
1.
1.
Yes, 1011. 1011. B. Yes, which is 11. It's B. Excellent. And finally, I have 1110.
D.
1110 is E. E, it is E. E is 14, right? That's the number 14, so it's E. So you see that, okay, we can actually easily convert from binary to hexadecimal, starting from the least significant, but we can group them. Okay, each group of 4 bits, we can convert it into 1 hexadecimal digit. We can do that only between binary and octal and binary and hexadecimal because they are related. Okay, I cannot do it this way between binary and decimal. Okay, I cannot do it like this between, because decimal is not related to binary. But octal and hexadecimal, the conversion is very easy and very quick. For this reason, many programmers, when they would like to deal with binary, they prefer to use hexadecimal because they know how to convert this between hexadecimal and binary, or sometimes from octal. They deal with octal because it's very easy. Okay, it's very convenient, okay, for them, okay, to use hexadecimal and octal because they use less digits than bits. You can see here I have 32 bits in binary, but these are only 8 digits in hexadecimal, only 8. They were 32 bits in binary, but they are actually only 8 digits in hexadecimal because every 4 bits will be just 1 digit in hexadecimal. Is this clear?
Doctor?
Yes.
Yes.
Is there a way to figure out how to convert the digits, or we just have to memorize it?
Well, you see that I showed you actually the way that to do the conversion, right? Okay, but now every 4 bits, if you would like to do it quickly, like 1001 to get the 9, one way to do it is just to add the weights. So this is 8 plus 0 plus 0 plus 1, it's 9. Okay, or you can just memorize that 1001 is equal to a 9. For example, 0111. Okay, look at these actually here, 4 bits. This is 1, this is plus 2 plus 4 is equal to 7, right? So you can do it like this, or you can just memorize that 0111 is equal to 7, okay? So it becomes very familiar. If you do the conversion, if you practice solving exercises at the end of chapter 1, for example, there are many exercises, many conversion examples. If you practice, it becomes familiar, okay? It becomes something which is simple and easy. This is why I told you, go back to the previous slide. Okay, go back to the previous slide, which is shown. I don't really want to go back now. Go back to the table that shows, okay, binary and hexadecimal and octal, and see how you can do the conversion. Try to memorize this table. It becomes actually easy and fast for you to do the conversions. Okay. But even if you don't memorize it, it's still actually, you can always go back to the binary, look at the weights, and just remember the weights, and you can do the conversion very quickly. Yes.
Are hexa and octal were invented just to simplify the binary, or?
They were actually invented, yes, to make it, rather than writing 32 bits in binary, it will be really dealing with ones and zeros. You can easily make a mistake, okay? You can actually make a mistake when you are actually typing them or writing them. You can actually make actually the 1 is 0 or a 0 a 1. So to avoid these mistakes, okay, hexadecimal and octal were invented for convenience because they are similar to binary. They actually are similar to binary, but it's actually very convenient, very easy. Okay, that how you can deal with hexadecimal and octal.
Doctor.
Yes.
In the 32-bit binary, do we have a least and most significant bit?
Do I have? Okay, now I'm going to. Okay, somebody actually is requesting control. Say that again one more time. What's your question again?
We have 33-bit binary, right?
Yes.
Do we have a least
if you have one extra bit, if you have one extra bit here, you can always insert zeros to the left. It does not change the value of the number, right? If you have actually here, if you would like to extend this number, you can always extend it with zeros.
Okay, because
does this answer your question?
No, because my thought is the far left is the most significant, and
Yes.
it should be 2 to the power of 31.
صحيح. Right.
Okay. Okay. Thank you.
All right. So, so back here, okay, let me just go back to my presentation. So if you would like to convert, okay, octal and hexadecimal to decimal, is very simple. Let me just actually finish this slide. I only have a few minutes left. So to convert, let us take a look at this example. Okay, 7204 in octal. You can see I'm writing 8 here to indicate that this is actually octal. You multiply 7 by 8 cube. You multiply the 2 by 8 square. This is just 0. Multiplied by 8 is just 0. And this is 4. If you do the math, then you will get actually 3,716. Now notice that this number is not 7,204 because it's not really decimal, it's octal. So I just read it as 7204. The decimal value is 3,716. You take a number, let us say in hexadecimal, you would like to convert it to decimal. Okay, so this is 3BA4 in hexadecimal. So hexadecimal here, you can see it's 16. So this 3 is multiplied by 16 cube. Okay, the B is 11. You can see the B here, right? It's 11. And it must be multiplied by 16 squared according to its position. A here is 10. It has to be multiplied by 16. And the 4 is just 4. So if you do the arithmetic, okay, you will get 15,268. So it's very easy to convert an octal number or a hexadecimal number to decimal. How about if I would like to do the opposite? I would like to convert a decimal number to octal or to hexadecimal. How do I do this? How do I convert a decimal to an octal?
Divide by 8 or 16.
Exactly, you divide. Yes, you repeatedly divide the decimal integer by 16. I will give you one example and I will stop at this slide. So let us say the number 422. I would like to convert the number 422 to hexadecimal. So in order to convert it to hexadecimal, I have to divide by 16 because 16 is the radix. So when you take here 422 and divide it by 16, you can use your calculator. You will get 26 point something, but this is integer division. So therefore you stop at 26. Forget about the fraction, 26. Now 26 multiplied by 16. Anyone has a calculator? 26 multiplied by 16? What is 26 multiplied by 16? Quickly.
416.
416. Type 422 minus 416. What do you get?
6.
You get the remainder, which is 6. So therefore, when you subtract 422 minus the 416, you get the remainder, which is 6. Now notice, because you are dividing by 16, the remainder has to be between 0 and 15. It cannot exceed 15, okay? Because you are dividing by 16. So this remainder is a digit. Now you take the quotient, which is 26, and divide it by 16, you get 1. But that's actually 1 multiplied by 16 is 16. So 26 minus the 16 is 10. 10 is A. So the remainder is A, which is 10. Finally, you take this 1 and divide it by 16. Now, when you divide 1 by 16, you get 0, 0 point something. But that's 0, integer division. And the remainder is the 1. So therefore, the least significant digit here is the 6. The most significant digit is the 1. And you stop when the quotient is 0. So we can now write that 422, this decimal number, is equal to 1A6 in hexadecimal and radix 16. If you want, you can convert it back. Now this 1 is multiplied by 16 squared. This 16 squared is actually 256. This A is 10 multiplied by 60, and this is 6. So add 256 plus 160 plus 6, you should really get the 422. You can always check that your conversion was done properly. Is this clear?
Doctor.
Yes.
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 تفضل.
If the second step was 8 and the quotient was half,
So the quotient here was what?
No, the second step.
26 divided by 16.
Yeah, the remainder was 8.
If a remainder equal to 8, you get the quotient is equal to 1.
No. I say if the remainder in the second step is 8.
Yes.
And
you take the quotient and divide by 16. It has nothing to do with the remainder. It's the quotient that you are dividing by 16.
Okay, so if the quotient is
so
8,
for example, if this were 24 divided by 16, if this were 24, not 26, you get actually here 1, and the remainder will be equal to 8. Fine. And then you have to take the 1 and divide it by 16.
So how
anything which is less than 16 divided by 16, you get 0. And if this numerator is less than the denominator, okay, you get actually the remainder is equal to whatever appears on top.
Okay, so if the quotient is half, then the remainder is 0.
The quotient is what?
If the quotient is half, the remainder is 0.
You cannot. These quotients are integers. You cannot actually get the quotient which is half.
Oh.
You cannot get 0.5 as a quotient.
Okay.
You can actually, for example, here you cannot actually get 0 point something. You get 0. That's it. And the remainder is whatever appears here on top.
Clear.
This is integer division. Okay. So that's it for today. Let me actually just pause the recording. Okay. So as I said, next time we're going to start. Yes. If you. Okay. So I'm going to